Good afternoon. We have already discussed about basics of dimension analysis and formation of dimensionless groups or five groups by using Buckingham theorem. So the next main task involves in dimension analysis is modeling and similitude. So you may have remembered that dimensional analysis technique is used to predict the performance of prototype by referring to the performance of model. So to do that, we have to consider the similarity between model and prototype. In general term, similarity is state fact or behavior of being similar between model and prototype. So if we define the similarity in more technical manner in related to the dimensional analysis, if any phi group or the non-dimensional parameter of a model is equal to the prototype, then the prototype has some similarity with the model. However, to have complete similarity between model and prototype, all relevant phi groups has to be similar or equal between model and prototype. But generally we consider the complete similarity is achieved when three similarities are fulfilled. That is, if geometric similarity, kinematic similarity and dynamic similarity have to be achieved to say that the prototype is similar to the model. So let us consider one by one to have better understanding. Geometric similarity is related with the geometrical shape and properties of model and prototype. However, a model and prototype are said to be geometrically similar if and only if all body dimensions in all three coordinates have the same linear ratio. This ratio is called as length ratio. It can be mathematically represented as Lm over Lp, where Lm is the length of model, Lp is length of prototype. So the ratio between model dimensions and the prototype dimensions is equal to the length ratio. If you refer this figure, you can see all the lengths are 10 times more than the model. All the lengths in prototype are 10 times more than the figure. But if you closely look at, you will see that the angle has no scaling. That is because angle alone is a non-dimensional parameter. So there's no scaling on the angle. So simply the geometric similarity is the similarity between model and prototype with respect to its dimension. Then the second is kinematic similarity. It requires that the model and prototype have the same length ratio and the same time ratio. Therefore, the velocity ratio will be same for both. So it can be mathematically represented as velocity ratio is equal to the velocity of the model divided by velocity of the prototype. So by simplifying it, you can say that the velocity of model is equal to the velocity ratio times prototype velocity. So in this figure, you can see all the model velocities at corresponding points are equal to the velocity at the corresponding point multiplied by a constant. So you can see that constant is beta. For the location 1, it's V1P is times beta is equal to V1M. At a particular location, the model velocity is equal to the velocity ratio times the prototype velocity. So you can see it in this figure. And in order to satisfy the kinematic similarity, it's essential to satisfy the geometric similarity. So geometric similarity is the similarity of the dimensions of model and prototype. kinematic similarity is the similarity of the velocity between model and prototype. So third is the dynamic similarity. In dynamic similarity, it relates with the forces on the model and prototype. If the ratio of the force acting at the corresponding point of the model and prototype are same, then it is said that the dynamic similarity exists between model and prototype. Similar to the length ratio and the velocity ratio, force ratio also can be defined in the similar manner. Fr is equal to Fm over Fp. Fm is the model force and the Fp is the force on prototype. So in this figure also you can see the Fdp is the force on the prototype and model force is equal to some ratio times prototype velocity. That ratio is called as force ratio. So complete similarity between a model and prototype is achieved only when all these three similarities, namely geometric similarity, kinematic similarity and dynamic similarity, are fulfilled. So if we summarize the process of dimensional analysis, so first we have to find the 5 groups. So there are one dependent 5 group with number of independent 5 groups. Suppose the dependent 5 group is phi 1 and independent 5 groups are phi 2, phi 3 and so on. Then the dependent 5 group, that is phi 1, is generally a function of other independent 5 groups. So it can be mathematically represented as phi 1 is a function of phi 2, phi 3, phi 4 and so on. Then to ensure the complete similarity, the model and prototype must be geometrically similar and all independent 5 groups must match between model and prototype, which means phi 2, phi 3, phi 4 and so on of the model have to be equal to the same 5 group of prototype. Then by matching independent 5 groups, we can calculate the parameters of prototype according to the model behavior. So then we can move to the dependent 5 group. Then by using all these results, we can match the dependent 5 group of model with prototype to calculate the values of dependent variables. So that it's the theory related to the dimensional analysis. First calculate the 5 groups, then match the similarities to find out the unknown variables from the model results. So hope you have understood the concept behind the dimensional analysis and model testing. So in order to have more clear understanding, let us consider one example. So in this example, you are asked to find the model velocity in the wind tunnel to achieve similarity between model and prototype. All the other relevant parameters are given as data. So try to work this out as a homework and let us meet next time with the solutions. Thank you.